Hey, so one day I had a dream, okay? And I want to tell you about it. So the dream I had was last summer, and I was just sleeping, dreaming, whatever. And suddenly I don't know, I was really taken in by this idea, okay? It's this idea that our entire universe, everything we conceive as being real, is actually just like a little thing floating on the edge of a large wave. Okay? So, what I mean by that is like this. It's like, have you ever gone and you're swimming in an ocean or something, and the waves are kind of calm, and there's big waves, and then you go and you like sprit some water on it or something, and then the waves, there's like these little tiny ripples on top of the bigger wave, and these little tiny ripples, they go and they connect with each other and they make other ripples, and it sort of ripples around and it creates its own little wave system that you've just done by just spritzing some water, uh, flicking the water. But you'll notice that it's completely unaffected by the larger wave, because the larger wave, on a calm day, it's just like this, and your little tiny ripples, they don't interact with that larger wave at all. And I think it would make a lot of sense if our entire universe, as we conceive it, is literally this entire process. So I was talking earlier, I think people were kind of interested in the idea that I think that we can probably move faster than the speed of light, because the double slit experiment, of course, shows that light knows what's in front of it, because otherwise, it would go off to the side. And in the experiment, they showed that if they put their finger out here, the light that would otherwise go to the side just goes and hits the finger. And how would it know that? The only way it would know that is if it could time travel, because it would have to literally travel faster than the speed of light uh, in order to uh, in order to reach that point. So, on a quantum physics level, because of quantum tunneling and because of the double slit experiment, we know that things can move faster than the speed of light. But on a general relativity level, on Einstein's theory, which is that there is a maximum speed in the universe, that's the speed of light, and everything, all of space time, moves relative to the speed of light. It's different. So we have this thing in physics right now where, on the one hand, there's Einstein's theory, and on the other hand, there's the quantum mechanics, which is entirely different. Now, to me, I think the clear sort of answer to this is the dream I had. And this dream was kind of crazy because I was just having this dream and it was just making so much sense to me. I think I kind of like woke up and I was lucid dreaming and I was kind of just thinking about this for like 8 hours. I wrote a whole thing about it. It's it's really an interesting concept that we ourselves are just this little ripple in the wave. So what I'm saying is that the Big Bang, every single proton, the nucleus, every single electron, all this sort of stuff, this is all just the ripple of some sort of flick on the greater currents, on the greater wave of life. So this would be a string theory concept where all the universe, all the dimensions, everything, it's just one unified sort of wave spreading out in multiple dimensions. And then we would be a sort of little flick in a little sort of pattern that's emerged. So, what's the evidence here? Okay, so I'll pull up some graphics. I'll add in to one side of me, and essentially there's this interesting thing in mathematics. It's called the Riemann hypothesis, and the Riemann hypothesis is the most famous unsolved problem in mathematics. And basically, what the Riemann hypothesis is there's this thing called the zeta function, which is basically a way of modeling numbers and just reality in like multiple dimensions. So it's like a way of just multi-dimensional modeling in mathematics, right? And the zeta function has something called the absolute zero line. Okay, so the core of the absolute zero line, hope I'm not losing you, is prime numbers. Okay, and they're sort of modified a little bit, and this is the absolute zero line, and there's this conjecture about it, all that, but I don't want to get into it, because what's really interesting about the uh, like the Riemann hypothesis and the zeta function, the absolute zero line, is that these absolute zeros, these absolute zeros on the absolute zero line, which are really just modified prime numbers, they are strongly like hypothesized to be linked to the eigenvalues. So what are the eigenvalues? So the eigenvalues have some sort of applications in quantum physics, but also they have applications the in the fields of statistics, okay? Because the eigenvalues, what they do is they actually decide what's absolutely random, right? That's interesting because you think of something that's absolutely random and it's completely random. But no, that's actually not quite the case. Things that are absolutely random, like random white noise, it has the way it's distributed in a space is determined by the eigenvalues. And the way we measure randomness in a statistical distribution is how similar or not, is this to the eigenvalues? Like there's some covariance here or something. What's going on? It's not matching our totally random like matrix, which would be determined by the eigenvalues. Okay, so this is very interesting, right? So we have something which is multidimensional modeling from the zeta function, which is like sort of a more mathematical concept. But the absolute zeros, the prime numbers, seem to add up to something which is related to quantum physics, the eigenvalues, and also statistics, literally what is random. And what is more intrinsic, I ask you, to the universe than what is completely random? I mean, to me, if something determines what is completely random, like that's sort of like the key to our whole universe, right? So, okay, how does this line up, right? So I think what's extremely interesting is that if you do a certain 4D, like Fourier transformation, it's called, of the zeta function, it looks exactly like a hydrogen atom. Now, why is that interesting, right? Well, hydrogen atom is actually, you might not know this, it's very interesting, it's actually a wave, okay? So they've shown that a hydrogen atom is actually small enough that it's considered a wave. It's not really considered like an atom in some contexts, it's just a wave. So, yeah, and then if you look at it, and I'll pull this up, right? Basically, the spinning on this transformation of the zeta function looks exactly like if you twisted it, and it looks like the GIF of someone took a video one time of a hydrogen atom, wave, and it looks exactly like this spinning. This spinning is going like this, right? And then if you look at the hydrogen atom, it looks like exactly like it. It's doing the same pattern, just flipped sideways, which really makes you think. Like it really makes you think. Is it possible, right? Is it possible that we, right? What if we're ripples in the great universe of life, okay? And our ripples are basically something like the zeta function. So let's say we live in a string theory universe, and let's say some grand maestro somewhere pulled the strings, okay? Like pulled the strings, and when these strings were pulled, things get tied up in little knots, okay, that move, multidimensional knots. So like these strings come together and they wrap up, and then they sort of create a reality, right? So what if that's what the Big Bang is? What if the Big Bang is these little strings, they get wrapped up, right? And then they move forward, and then they sort of like separate out, but there's still little like tiny little bits tied together. Like, I don't know how to like, what's that thing? It's like this confetti, or like, the thing where you can like shoot slime at people, those slime guns. It's like you shoot them and they turn into these little balls that like sprinkle off. It's like that. What if each proton, what if each nucleus in an atom, what if it's just the sort of these little like offshoots from the Big Bang, from the original mixture of everything? Or maybe it's the Big Bang didn't even happen, who knows? But like, what if these protons just are all just this little mixed up, and they're mixed up in multidimensional space? Okay, but what is relevant here is from our perspective, we see the protons as real. We only interact in basically 3, maybe 4 dimensions, like as we can perceive it. But what if there's actually many dimensions, they're all wrapped together? And what if, for instance, like, I'll just throw some thoughts at you. So throw some thought bombs at you, okay? What if electrons, because they say that, some people say, oh, there's true randomness in the universe because electron distribution is totally random. What if it's actually the case that what's totally random is correlated, okay, with the eigenvalues, which is correlated with the sort of pattern that created all of us? Like, what if the pattern that created all of us was related to the zeta function? That was the pattern of waves, okay, that came together, the zeta function, and it created everything. It's like boom, boom, boom. It's like the first evolution. It's just like self-replicating wave, and it came in, and this wave, sort of the way it transforms, it like self-replicates itself a whole bunch, and then slowly decays over time, and then that would actually explain nuclear decay, because these sort of, after a certain amount of time, there's a bunch of other waves in the universe, and they interact. And if a wave hits our wave at just the right point, it would sort of unwind. Okay, so we would just be a bunch of little waves. Then what we perceive as, yeah, the proton is just, we're only seeing a few dimensions of it. And to get back to what I was saying, the electrons, right, are not actually totally random in this theory. Okay, electrons would be moving in multidimensional space, and they would just be moving in and out, and they would be moving in that same pattern that we qualify as being totally random. That's our random pattern, but actually that is the pattern which is like constructs all of life, right? This would be the idea. And I think it would make sense for a lot of reasons. So imagine the double slit experiment, where it seems like light somehow knows what's happening in the future. What if it's the case, right, that what we perceive to be light is actually moving, like the light is actually moving like this. This is the pattern of light. It's very high up, whatever. But what we can see is just this central bound. And we operate, for the most part, in this central bound. Because similar to this, right, in a pool, okay, you have this, like an ocean or something on a calm day, you have this big wave, okay, big wave. And if you sprinkle some water on that big wave is never impacting your little ripples, because your little ripples are operating, they're just on a totally different frequency, man. Like, these two things don't interact. This one's huge, this one's so small, they just pass right by each other. What if it's possible that anything that goes past the speed of light just goes right by us? Like, I'm telling you, like, it doesn't even interact with our bodies. Because think about this, right? What if what we perceive to be mass is not actually mass? What if each proton, which each atom, every compound in our body, it is made up of a multidimensional mass. And when something hits this, okay, like when you are hit in this direction, there's no actual such thing as mass, but when it hits you, there's a sort of like, the way the pattern is, it sort of like redirects, like in this sideways pattern, whatever, boom, 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 and then it like comes back, and then this pattern is redirected this way, boom, 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 and it sort of like, so when you hit, it appears as if there's mass, but actually, maybe there is no mass. It's just that, it's just our perception. We perceive mass because of the difficulty of, if this small little wave is hitting this big wave, then it's like that big wave ain't moving, like what if we, like, what if when I do this, actually my hand, like waves totally move through that hand, and waves move this way, and all this sort of stuff happened, but in our perception, in our little slice of reality that we can perceive, that match our pattern, that is like the same sort of wave size, it's like it appears that there's mass just because of how the waves move. Okay, so that would be the sort of theory, and I think that just makes a lot of sense for a lot of different reasons. Like, we clearly have these hydrogen waves. In physics, there's also these, in chemistry, there's these like quantum states. There's different levels of quantum states, and it's like a shell, and this shell moves in this sort of pattern. What if that's just multiple zeta functions coming together, and then that makes all these patterns? And what if the absolute zero line is like, those are making up randomness in our universe, because our entire universe could fundamentally be constructed on this zeta function wave, right, which is interacting, and then it's interacting with you, and it's interacting with everything, but we're only perceiving this idea of mass, which is just an illusion. Mass would be an illusion here, because it's just the waves, as I said, and it makes sense for so many reasons. Let me give you another one. So I talked before about this thing called the relativistic Doppler shift. So the Doppler shift, in general, is just this idea that, so just a regular Doppler shift is like, when you speak in an environment, you sort of speak, and then as you, like, if you just emit regular waves and you're heading in a direction, like the waves get more spaced out, you see, because over here the waves are all close. Even like you're just emitting waves at a regular point, you're traveling, right? And then as you get further away, the waves become wide and more spaced. And so that's something that describes how sound works, because things will sound differently the farther are away from them. Like echo, echo. That's what the Doppler shift is. Okay, but the relativistic Doppler shift is something entirely different, which is actually bizarre. Okay, and the relativistic Doppler shift, well, there's different things that it means, but one of them is that if you put light through a prism, okay, if light goes through a prism, and let's say it's a rainbow that you're shooting into a prism, you're shooting a rainbow into a prism, and then let's say it reflects sideways. And if you reflect it at the right sort of angle, what will happen in this prism is the light will flip, so it will become like, oh, now it's only like, now the blue light is before the red light, but before the red light was before the blue light. It'll switch up. And technically that switch up, right, is actually faster than the speed of light, because like just the way it works. And physicists say like, oh, this is causality, this sort of little switch up. Like it doesn't break causality or something. I think all this causality stuff is total nonsense. I don't think, what's causal to what? Is our universe constructed on this idea of things can't cause things? I don't know. I think that's so arbitrary, and I think intuitively as human beings, like, we know that's not how it actually works. Like, waves make total sense, okay, but this sort of causality stuff, I don't know. I don't know why people think this way. It's kind of confusing to me. But essentially, yeah, they say this doesn't break causality, so it doesn't do anything. And I don't know, they come up with like weird math for how it would work, something related to electromagnetic spectrum, something, and then that's why these colors can switch. But actually, right, would this not make more sense, right? Imagine this, right? If light can go faster than the speed of light, and if you're going through this prism, and this prism is reflecting your light in some way through this like overall pattern, and basically you're getting like, the way the pattern interacts with you, it's like you get sped up. Like, so your light, either the wavelength increases or the frequency increases, and essentially that light in which the wavelength, because the speed of light, is determined by the wavelength and the frequency. So the wavelength and the frequency, if it gets too high, my hypothesis here would be that it would still actually exist. It would just sort of go into like the greater realm of the universe, outside of our little like bubble where it's interacting with all the big waves, and stuff is happening. And then but as it goes forward, right, it's the same way like light works. Like, imagine you have a boat and there's waves in front of you, okay? So these waves in front of you, you're pushing them forward, okay? But the waves behind, like, you're kind of actually slowing them down a little bit, because they're sort of like in your wake, and they're not being tugged around, like maybe they're moving backwards. So would it be possible that the actual reason why, because I think red is slower than blue, I think is how it works. It's a little bit confusing to me. I should probably know that. But what if it's the case that like we're getting the red light in the relativistic Doppler shift back, because the blue light is leaving the system, and then the red light that is existing, it used to be more like bluer light, and then it's just sort of being like, because of this transformation, because it's going faster, like a boat, okay, like a boat, the waves behind it are slowing down, okay, in order like right behind the boat, like it's slower, because and that's the red light coming back to us. So what we perceive as the relativistic Doppler shift, maybe that's just a case of the sort of boat leaving us some red light behind, and the blue light just totally leaving the system, and then maybe like energy is conserved or something, but really it's a bit of an exchange. We just don't notice it. So I think that's an interesting thought. And yeah, that would just make sense for so many different reasons. Like, consider this too. Every single compound has an electromagnetic like has a sort of spectrum where if you hit it at an exact certain way, then it will return a like, what's it called? It will return a light molecule to you, like it'll return a photon to you. So it's like, to me, this just totally screams of like, you're hitting at the perfect point where it's like, because if you imagine the zeta function as this wave, okay, and then you hit it at the exact perfect point, and then it would spin off another zeta function or like something like that, and it would create this photon that goes sideways. It's like if you just hit it at the exact right spot because of the the constructive and deconstructive properties of waves. So yeah, that's just my overall idea of physics, and I think that makes sense, and I think that would totally bridge the gap between like the idea of quantum physics and also the like relativity and stuff like that. And I think that's probably just what's happening. And yeah, I don't know. I trust in the dream, guys. So yeah, there's some more insight into that. And I think that if we could make that sort of thing work, this would totally imply basically this theory of physics that if we hit this wave at the right point that makes our universe, we could totally do like crazy things. Like imagine this, right? If we could construct some sort of theory of the universe where waves were able to like if they collided into each other at the perfect point, for example, like if each hydrogen atom was like a zeta function wave, right? If that was the case, then if we hit it at the exact right point, at the exact right time, then what we'll end up with is this sort of, what is it, like, we could like deconstruct the wave, we could make the wave go faster, we could even do something where we make the wave go faster and then we send like another wave to like intercept it to make it go slower again, and we could send like cross-dimensional messages. We could, then of course it would only be a short while, we could like transport people across time, we could create wormholes, we could do all sorts of crazy stuff because we would basically be traveling through like the outer layer of the universe, right? Because we exist within this certain confines of the waves that constitute our universe. But if we were able to sort of send waves through different dimensions and then curve it back into our reality, we could do time travel. We could do all this sorts of crazy stuff, which modern physics is like, oh, that's impossible. But the fact that there is quantum tunneling, the fact that there is a double slit experiment, I don't know. A lot of the physicists, I don't know, at least the ones I interact with, there's probably the cooler ones, just the ones like I see online or whatever. I don't know, they're so negative about it. They're like, no, everything's random, it's impossible, blah, 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 blah. But I think that they're just so pessimistic. Like, I think that this makes a lot of sense. And waves are just so natural to us. I guess to just sort of finish off the video, like if I go like this is so natural to me. It's like a wave is passing right through me, right? And it's like, I think what is unnatural is going like this. That takes so much effort to do because I'm having to stop the wave, like if I go like this, it's so natural. Waves totally intuitively make sense to my mind. I think they make sense to everybody's mind. And one more thing I will leave you with, okay? There's this thing called Lesage gravity. So instead of having the Einstein theory of gravity, there's this thing called Lesage gravity. Lesage gravity is imagine if in the outer universe of all the waves that are huge or whatever, what if there was what if it was raining? What if there was little sprinkles of rain on top of our little droplets and they were interacting with it? Well, imagine that these things, because there's an infinite amount of waves in the universe going at an infinite amount of speed, theoretically, imagine some of them will end up hitting our universe, right? And imagine if you had two balls like this, right? And there's an infinite amount of waves hitting from infinite amount of areas, right? So if you were just like this, you actually wouldn't move at all because they would be, because there's an infinite amount of them, they go an infinite number of directions, they would just end up right in the middle, right? But if you took another one, then suddenly, the waves can't come from this direction. So these things would slowly come together, right? And that's called Lesage gravity, right? And that would also line up perfectly with a sort of like infinite wave, a theory of the universe. So I leave you with that. It's good to ponder.